Hi all, welcome back to the lecture on quantum mechanics. So in the last two sessions, we have introduced the time dependence on the equation, the wave function, and as well as the interpretation of quantum mechanics. Now, from here onwards, we'll be focusing on one special aspect. It's called time independence from the equation. So we can just recall what we have discussed so far. So we have discussed in quantum mechanics, the state of the system is represented by the wave function, and the equation of motion in quantum mechanics is time dependent from the equation, which is given as minus h bar square by 2m dou square psi by dou x square plus v of x t psi of x t equal to I h cross dou psi by dou t. So it is the second order differential equation space, and it is first order in time. Okay. Now, hereafter we are going to consider a special case. Suppose this potential, so this V of xt is the potential of the system, and the potential experienced by the system. Then, if this potential is independent on time, the potential is independent of time. That means if the potential is only function of position, then it is easy to solve this kind of differential equation. So this differential equation, this time dependence on the equation can be solved by using the variable separable method. So that means you can just write the wave function psi of xt as a product of two functions, the psi of x and phi of t. Okay, so the wave function, which is the function of both position and time, I am written as capital psi, and the psi, which is only function of x, is smaller psi. So that is why have differentiated, distinguished these two variables. Okay, so if this if you divide, or if you using this variable separable method, then what will be our Schrodinger equation? So recall the Schrodinger equation is minus h bar square by 2m dou square by dou x square acting on psi of xt. So here psi of xt can be written as a function of x and function of time, plus now potential is only function of x, and psi of xt again divided as psi of x plus phi of t equal to ih cross dou by dou t psi of x phi of t. Okay, now here it is a partial derivative, and this partial derivative will act only on psi of x. This phi of t can be taken outside, so this can be written as phi of t minus h cross square by 2m dou square psi by dou x square plus v of x psi of x phi of t. And the right hand side is a derivative with respect to time. So in that case, the function which is depending upon position can be taken outside. It will be a constant in that derivative. So psi of x plus I h cross dou phi by dou t. Now I am going to divide this entire equation with psi of x phi of t. Just divide it with this. Then this become, on left side we have 1 by psi of x minus h cross square by 2m dou square psi by dou x square plus v of x equal to 1 by phi of t ih cross dou phi by dou t. Now just highlight this equation. So if you look at this particular equation, now the specialty is here the left side contains only x and the right side contains only t. Now in order to validate this equation, both LHS and RHS must be independent on x and t. If it is depending upon the x and t, then this equation will not be valid, because the left, if the left side is function of x and the right side is function of time, then keeping time constant we can vary x, then obviously this equation will not be valid. So the LHS will vary with the RHS is remaining as a constant, so that is not possible. So obviously, in order to validate this equation, both sides must be constant. So in that way, we can write that constant as E for the time being. Okay. Now, what is E that we don't know? What is the meaning of E that we don't know at this moment? That we'll find out later. Okay. Now, if you equate both LHS and RHS is equal to E, then we can write 1 upon phi of t IH cross dou phi by dou t is equal to E. Now remember here phi is only function of time, so there is no need to put the partial derivative. Instead we can have the total derivative itself. So this become IH cross d phi by dt equal to E phi. Now we can solve this is a simple differential equation. We can solve it. We can just integrate it, and if you integrate this phi of t will be exponential of minus IAT by h cross. This will be the solution. And there will be some integration constant. I am not going to consider the integration constant for the time being because that can be absorbed into psi of x. So that is why I am not going to consider the integration constant for the time being. Okay. So the finally, if this phi of t is of this form, then what was our solution? So recall our the wave function psi of x t is psi of x times phi of t. Now we have found the form of phi of t. The phi of t is exponential minus I e t by h cross. So therefore the psi of x t now can be written as the psi of x, the function of x times e raised to minus I e t by h cross. Okay. Now, so here this phi of t we have found by equating the RHS to E. Now, similarly, we can find psi of x by equating this LHS of this equation to E. So, if you equate the LHS to E, then we'll get a new equation. So that equation can be written of this one. So here, what I have simply done is I have just equated the left hand side equal to E. Just equate this LHS part equal to E, and I have taken this psi of I will just multiply this entire equation with psi of x, then I will get this equation. So this equation is hereafter known as time independent Schrodinger equation. Okay, so we can find this psi of x by solving this equation, the time independence from the equation. Now solving this equation is not that much easy because there is no general way of solving it. Only depending upon the functional form of v of x, we have to employ different methods to solve this kind of differential equation. So it will be very easy to solve this differential equation if v of x is 0. That is called free particle case that we'll discuss later. Okay, and if v of x become complex, then the complexity of differential equation, uh, the 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 difficulty level of solving differential equation will be higher. Okay, so by solving this differential equation, the time independence from the equation will get psi of x. So therefore, the total state or the total wave function psi of xt, I can write as psi of x e raised to minus I e t by h cross. Now the state which is represented in this form is called the stationary state. So stationary state contains two parts. One is the solution of a time independence from the equation, and second one is one exponential part. This part we can call it as the phase part, or it is basically called a dynamical phase part of the wave function. Why it is called dynamical? Because this part it evolves time. So when time increases, this changes, but it is e raised to minus psi, so it is possibly vary from -1 to +1. Okay, now what are the peculiarities of this stationary state? Okay, now I will just recall what we have discussed in now. If this potential, if it is only function of position, if v is only function of position and it is not function of time. Then instead of time dependence from the equation, we can solve the time independence from the equation, and we can find psi of x from it. And once you find psi of x, the total solution would be psi of x t equal to psi of x e raised to minus I e t by h cross. Okay, now this state is called stationary state. Now why it is called stationary? So what are the characteristics of this stationary state? The first thing is its probability density is constant in time. So if you look at this wave function, so remember this wave function psi of xt is psi of x e raised to minus I e t by h cross. Okay. Now what would be psi of x0? It would be psi of x1. Okay. If you look at the mod square of psi of xt, that would be equal to mod psi of x square, which is same as mod psi of x0 square. Okay, so what this means, so here the left side is a probability density at time t, and the right side is a probability density at time 0. So both are same. That means the probability density is not changing with time, it is constant in time. So that is the one of the characteristics of stationary state. So in case of stationary state, the probability density will remain constant. Now the second thing is the expectation value of any operator is also constant in time. So recall we have discussed what is meant by expectation value while discussing the formulation of quantum mechanics. So in quantum mechanically, all measurement is represented by operator, and the result of measurement would be the expectation value of operator, and usually denoted by this symbol. Okay, so the all measurement is a Hermitian operator, and result of measurement would be the expectation value of operator. So the expectation value of operator is defined as its integral psi star of xt a psi of xt d cube x. Okay, in case of one dimension, only one axis. You just substitute. So it would be integral psi star of xt would become psi of x a raised to plus I e t by h cross, psi star of x a raised to plus I e t by h cross. Then we have operator a, then psi of x a raised to minus I e t by h cross dx. So this exponential factors would cancel the product of e raised to plus I e t by h cross and e raised to minus I e t by h cross. That would cancel each other, and this become simply integral psi star of x operator a psi of x dx. So here you can see that in this integration there is no time involved, so the right hand side is not a function of time. So the expectation value would be constant in time. So we have discussed two things, two characteristics of stationary state. The first of all, its probability density is constant in time, and as well as the result of all measurement, it is constant in time. There is no time evolution for a measurement, the measured value in if the system is in the exactly in the stationary state. Now the third one, there is one very important point. It is the eigenstate of Hamiltonian, or the stationary state is also known as the energy eigenstate. Okay. Now, in order to understand that, we can just recall the Hamiltonian in classical physics. Hamiltonian of conserved system. So the Hamiltonian of conserved system, usually we'll write p square by 2 means kinetic energy plus potential energy. Now, according to quantum mechanics, this momentum is an operator, and momentum operator can be represented as minus AH cross tau by tau x, and the position operator is simply x. So p x. So so this is the classical Hamiltonian. When you're going to quantum mechanics, you have to just replace the classical canonical variable into a quantum mechanical operator. So the Hamiltonian h cap would become p square by 2m plus v of x. Now this can be written as this p square would be minus h bar square dou square by dou x square. So that is also 2m. So minus h bar square by 2m dou square by dou x square plus v of x. So if this h is acting on psi of x, it will become minus h bar square by 2m dou square psi by dou x square plus v of x psi of x. Now, using we know that in time dependence from the equation, this quantity is equal to E times psi of x. So just rewind what we discussed earlier. So this is the time independence from the equation. So minus h bar square by 2m dou square psi by dou x square plus v of x psi of x is equal to E psi. Okay, so if you're using that result, then this h psi of x would become E psi of x. Okay, so what we are getting is, so let us just simply move this part. So what we have got is the Hamiltonian acting on psi of x is minus h cross square by 2m dou square psi by dou x square plus v of x psi of x, and it is same as E times psi of x. So that means h psi of x is equal to E psi of x. And what this means, the Hamiltonian acting on psi of x gives psi of x with a multiplication factor. So this shows that the psi of x is the eigenstate of Hamiltonian corresponding to the eigenvalue E. So the psi of x is eigenstate of Hamiltonian corresponding to eigenvalue E. Now usually the eigenvalue of Hamiltonian is known as energy, and therefore the psi of x now hereafter can also be called as the energy eigenstate. So because the psi of x is basically a stationary state, it is the eigenstate of Hamiltonian, or simply it is called as energy eigenstate. Okay, so this is the third property. So the first two property is basically depending upon the time dependency of the probability density and the expectation value of operator. And the third one, third characteristic shows that it is the stationary state is nothing but the energy eigenstate. Now, since the psi of x is identified as the energy eigenstate, then we can use the superposition principle to find the general solution. So we have the time dependence from the equation, time independence from the equation as h psi of x is equal to E psi of x. Now this is a differential equation, so there can be more than one possible solution. So we can have the solution like psi 1x, psi 2 of x, psi 3 of x, etc. are energy eigenstate corresponding to the energy E1, E2, E3, etc. So that means this H acting on psi 1 of x gives E1 psi 1 of x, and H acting on psi 2 of x becomes E2 psi 2 of x, etc. So in one system there can be multiple energy state. For example, in case of hydrogen atom, there are many stationary orbits corresponding to n equal to 1, n equal to 2, n equal to 3, etc. Similarly, for any system, there can be multiple energy states. So let the psi 1, psi 2, psi 3, etc. are the different energy states. Then the corresponding the state can be written as psi 1 of xt as psi 1 of x e raised to minus I e1 t by h cross, and psi 2 of xt would be psi 2 of x e raised to minus I e2 t by h cross, etc. And psi n of xt is psi n of x e raised to minus I e n t by h cross. Now all these are the solutions of time dependent Schrodinger equation, and it is a linear differential equation. Now we know that the property of linear differential equation, that if it has multiple solution, then the superposition of solution is also another possible solution. So since psi 1, psi 2, psi 3, etc. up to psi n are the various possible solutions of the Schrodinger equation, so therefore a general solution psi of xt can be written as psi 1 of xt plus psi 2 of xt plus etc. psi n of xt. Okay, it may have up to infinite terms, or this can be written as in a compact form. It is sum over n equal to 1 to infinity. So just multiply each of these coefficient with some constant. Here c1, c2, cn, etc. Then this can be written as sum over n equal to 1 to infinity cn psi n of x e raised to minus I e n t by h cross. So this would be the general solution. Okay, so what actually we are going to try from this result. So what is the advantage of this result? So that we can see now. Okay, so we suppose we have some a general potential v of x, which it is independent on time, and to find the exact solution we have to solve the time dependence Schrodinger equation, that is usually called the Schrodinger equation. So we have to solve the Schrodinger equation to find psi of x. Now the direct solution of this psi of xt would be very tedious task. Since it is independent of time, we can try to solve the time independent Schrodinger equation and find the possible psi of x. So once you find the possible psi of x, that is psi 1 of x, psi 2 of x, etc., corresponding to the energy eigenvalue E1, E2, etc., then the general solution can be that psi of x equals sum over n equal to 1 to infinity Cn sin n of x e raised to minus I e n t by h cross. So the solution can be written by simply finding the the stationary wave function, the stationary state. So we can summarize once again. So if v simply is function of v of x, then first we'll solve the time independence from the equation and find psi 1, psi 2, etc. corresponding to the energy eigenvalue E1, E2, etc. Then the general solution would be psi of x t psi n equal to 1 by Cn psi n of x e raised to minus I e n t by h cross. Now the Cn is unknown for the time being. Now the Cn we can find by knowing the initial condition. So if you know some initial conditions, the value of a function might equal to 0 or its derivative, etc. So depending upon the number of coefficients we need several initial conditions. So if we have two unknowns, then by knowing the two initial conditions we'll be getting the coefficients. Okay, so anyhow, this if not if you know the initial condition, there is psi at time 0, then we can just substitute that condition into the general solution. So in that case, this e raised to minus I n t by h cross would vanish because e raised to 0 is 1. And by solving this equation, it would be possible to find the Cn. Okay, so we'll illustrate this solving in this method using one example in the next class. Okay, so this is all about the stationary state. Okay, so remember, if the potential is only function of v of x, then instead of the time dependence from the equation, we can use the time independence from the equation, which is given as minus h bar square by 2m dou square psi by dou x square plus v of x psi of x is equal to e psi of x. So hereafter e is energy and the psi of x is the energy eigenstate, because h acting on psi of x is psi of x. So a general then the time dependent state psi of xt, by including the time factor, it can be written as psi of x e raised to minus I e t by h cross. Now this state is called stationary state. And what are the peculiarities of the stationary state or energy state? The first one is mod psi square is constant, is not function of time, and the expectation value of operator is not function of time, and it is the eigenstate of the Hamiltonian, or it is the energy eigenstate. And finally, the general state psi of xt can be written as a superposition of the energy eigenstate. Okay, so this is a general solution. Now from here we have to find this coefficients, and this coefficient can be found from the initial condition. Okay, so that's all for now. The time independence from the equation and as well as the stationary state. In the next class, we'll try to solve one numerical based on this. So that will give some overall idea about the use of the stationary states for finding the general solution. Okay, so thanks for watching this video. We'll see you in the next class.